Assalamualaikum. I am the group leader of Fundamentals of Traffic Flow and Green Theory. This is our report. Introduction is it is important to realize that the primary function of a highway is to provide mobility. This mobility must be provided with safety in mind while achieving an acceptable level of performance, such as acceptable vehicle speeds. Many of the safety related aspects of highway design we discussed in chapter 2. And focus is now shifted to measures of performance. The analysis of vehicle traffic provides the basis of measuring the operating performance of highways in undertakings such as analysis the various dimensions of traffic such as number of vehicles per unit time or flow. Vehicle types of vehicle speeds and the variation in traffic flow over time must be addressed because they all influence highway design. The selection of the number of lanes, pavements, types, and geometric design and highway operations, selection of traffic control devices including signs, markings, and traffic signals, both of which impact the performance of the highway. In light of this, it is important of the analysis of a traffic to begin with theoretically consisting quantitative techniques that can be used to model traffic flow, speed, and temporal fluctuations. The intent of this chapter is to focus on models of traffic flow and creating this providing the groundwork for quantifying measures of performance and levels of services which will be discussed in this chapter 6 and 7. Traffic stream parameters. Traffic stream can be characterized by a number of different operational performance measures. Before commencing with a discussion of the specific measures, it is important to provide definitions for the context in which the measures apply. A traffic stream that operates free from the influence of such traffic control devices as signals and stop signs that justify and interrupt flow. This type of traffic flow is the influence primarily by roadway characteristics and the interactions of the vehicles in the traffic stream. Freeways, conditions, mid-lanes, highways, and two-lanes highways of operating under uninterrupted flow conditions. Traffic streams that operate under the influence of signals and stop signs are classified as interrupted flow. Although all the concepts in this chapter are generally acceptable for both types of flow, there are some additionals. The complexities involved the analysis of traffic law at signalized and unsignalized interactions. Chapter 7 will address the additional complexities relating to the analysis of traffic law at signalized intersections. For details on the analysis of traffic law at unsignalized interactions, refer to other sources. Transporting Research Board 1975 to 2000, it should be noted that environmental conditions, day versus night, sunny versus rainy, and etc., can also affect the flow of traffic, but is issues beyond the scope of this book. The traffic flow speed and density. The traffic flow speed and density are variables that form the underpinnings of traffic analysis. To begin study of these variables, the basic definitions of traffic flow speed and density must be presented. The traffic flow is defined as the Q is the traffic flow in the vehicles per unit and time. The N is the number of vehicles passing some designated roadway point during time, and the T is duration of the time interval. Though this flow is often measured over the course of an hour, in which case the resulting value is typically referred to as volume. Thus, when the term volume is used, it is generally understood that the corresponding value is in units of vehicles per hour. The definition of flow is more generalized to account for measurable for vehicles over any period of time. In practice, the analysis flow rate is usually based on the peak 15 minutes flow within the hour of interest. This aspect will be described in more detail in chapter 6. Aside from knowing the total number of vehicles passing a point in some time interval, the amount of time between the passing of successive vehicles or time between the arrival of successive vehicles is also interest. The time between the passage of the front bumpers is successive vehicles at some designated highway point is known as the time headway. The time headway is related to T as defined in this equation. So where T is duration of time interval and the H sub I time headway of the ITH vehicle, the elapsed time between the arrivals of the vehicles I and 1 And the N is the number of measured vehicle time headways at some designated roadway point. In substituting equation 5.2 into equation 5.1, this is where H is at the average time headways. The change of H is the average time headways in unit time per vehicle. The importance of the time headways in traffic analysis will be given additional attention for forthcoming sections for this chapter. The average traffic speed is defined in two ways. The first is the arithmetic mean of the vehicle speeds observed at some designated point along the roadway. This is referred to as the time mean speed and is expressed as where the change of use of time is time mean spent in unit distance per unit time, where the spot speed, the speed of the vehicle at the designated point on the highway as might be obtained using a radar gun or the ITH vehicle. And the N is the number of measured vehicle spot speeds. The second definition of speed is more useful in the context of traffic analysis and determined on the basics of the necessary for a vehicle to travel some known length of roadway. This measure of average traffic speed is referred to as the space mean speed and expressed as assuming that the travel time for all which vehicle is measured over the time length of roadway. Where the change of time is space mean speed in units distance per unit time, and the L is the length of the roadway used for travel this measurement of vehicles, and the change of time is the average vehicle travel time distance. So where the T sub I is the time necessarily for vehicle where I to travel a roadway section of length, and the N is the number of measured vehicle travel times, which is the harmonic mean of speed. Space means speed. Space means speed is the speed variable used in the traffic models. So these are the formulas that you can use of using the space mean speed. So for the example, the speeds of 5 vehicles were measured within radar at the midpoint of a 0.5 mile or 0.8 kilometer section of roadway. The speeds for vehicles 1, 2, 3, 4, and 5 were 44, 42, 51, and 49, and 64, 46 miles per hour, or 70.8, 67.6, 82.1, 78.8, and 74 kilometers per hour, if it represents by kilometers. Respectively, assuming all vehicles are traveling at the constant speed over this roadway section, calculate the time mean space means speed. So we can use the formula that are given us for the time mean speed. So the equation of 5.5 is applied using this formula. You can substitute each speed of the vehicles by 44 plus 42 plus 40, 51 plus 49 plus 46, then divide it by 5. So the answer is 46.4 miles per hour. So the space mean speed will be applied. This equation is based on the travel time. However, because it is known that the vehicles were traveling at constant speed, we can rearrange the equation to utilize the measure of speed, knowing the distance L divided by the time is equal to the speed. So length over time was the speed. So note that the space mean speed will always be lower than the time when time mean speed, unless all vehicles are traveling at the exact same speed, in which the case two measures will be equal. So finally, the traffic density is defined as K equals to N over L, where the K is represents as the traffic density in vehicles per unit distance, and the N is the number of vehicles occupying some length of roadway or some specified time, and the L is the length of the roadway. So the density can also be related to the individual spacing between successive vehicles, so which measured from the bumper to front bumper, the roadway length, and can be defined as where S sub I is spacing of the I vehicle and the distance between the vehicles I and 1. measured from the bumper to front bumper. And when you substitute it, it can relate to average spacing in unit distance per vehicle, time, headway, and spacing are referred at as microscopic measures because they describe a characteristic specific to individual pairs of vehicles within the traffic stream. Measures that describe the traffic stream as a whole, such as flow average speed, density, and referred as a measure, macroscopic measure. As indicated by the preceding equations, the microscopic measures can be aggregated and related to the microscopic measure. Based on the definitions presented, a simple identity provides the basic relationship among traffic flow, speed, space mean, and density, denoting space mean speed, change of space, as simply U for notational convenience, where the Q is the flow or typical in units of vehicle per hour, or the U is the speed, space mean speeds, typically in units of miles per hour or kilometer per hour. And the K is the density of the typical in unit of vehicle per mile and the vehicle per kilometer. So for this example, 5.2, vehicles time headways and spacing were measured at a point along a highway from a single lane over the course of an hour. The average values were calculated as 2.5 seconds per vehicle for headway and 200 feet per vehicle, or 61 miles per vehicle for spacing. Calculate the average speed of the traffic. So we will calculate the average speed of this traffic. So the solution is to calculate the average speed of the traffic. The fundamental relationship in use is to begin the flow of a density used is need to be calculated for the headway with spacing data. Flow is determined. So you will substitute the H value of this represents because the data were collected for an hour. So we'll substitute the 2.5 second per vehicle equals to 0.40. The Q, the flow of typical units, or applying the spacing of the course of 1 mile. K equals to 0.005 vehicle per feet times by 5,280 feet per mile equals to 26.4 vehicle per mile. Now apply the, after arranging to solve for speed, gives this is equation, which is 1,440 vehicle per hour divided by 26.4 vehicle per mile equals to 54.5 vehicle per mile. So gisubstitute na niya yung bali mile per hour na lang kasi cancel itong vehicle sa taas at sa baba. Note that the average speed of the traffic can be determined directly from the average headway and spacing values as follows. So this is another formula. So 200 feet per vehicle divided by 2.5 seconds per vehicle. So the answer is 80 feet per second or 54 miles per hour, 0.5 miles per hour. So the basic traffic stream models, while the preceding definitions and relations provide the basis for the measurement and calculations of traffic stream parameters, it is essential to also understand the interaction of the individual microscopic measures in order to analyze the operational performance of the traffic stream. The model that describes these interactions are discussed in the following sections. It will be shown in this figure. Serves the important function of linking specific models of traffic into a consistent generalized model. The speed of density model, the most initiative starting point for developing a consistent and generalized traffic model, is to focus on the relation between speed and density. To begin, consider a section of highway with only a single vehicle on it. Under these conditions, the density will be very low and the driver will be also to travel freely into a speed close to the design speed of the highway. This speed is referred to as the free flow speed because vehicle is not inhibited by the presence of other vehicles. As more and more vehicles begin to use a section of highway, the traffic density will increase and the average operation speed of vehicles will decline from the free flow values as drivers slow to allow for the maneuvers of other vehicles. Eventually, the highway section will become congested with such a high density that the traffic will become to stop. And the density will be determined by the length of the vehicles and the space the drivers leave between them. This high density condition is referred to as jam density. One possible representation of the process is described as is the linear relationship in this figure. Mathematically, such as relation can be expressed. In this formula, where u is the space mean speed in miles per hour or kilometer per hour, the u sub f is the free flow speed in miles per hour or kilometer per hour. The k is the density of vehicles per miles or vehicles per kilometer, and the k sub j is the jam density in vehicle per mile or vehicle per kilometer. The advantage of using a linear representation of the speed density relationship is that this provides a basic insight in the relationship among traffic flow, speed, and density interactions without having the insight included by the additional complexity that a nonlinear speed density relationship introduces. However, it is important to note that the field studies have shown that the speed density relationship tends to be nonlinear at low density and high densities, those that approach the jam density. In fact, the overall speed density relationship is better represented by three relationships. Number one is a non-linear relationship at lower densities that a speed slowly declining from the free flow value. Number two, a linear relationship over the large medium density region or speed declining linearly with density as shown. And number three, a non-linear relationship near the jam density as the jam speed asymptotically approaches zero, which increasing this density for the purpose of exposition represent only traffic stream models that are based on the assumption of a linear speed density relationship. Examples of nonlinear speed density relations are provided elsewhere Pipes in 1967 and Drew in 1965. In flow density model, using the assumption of a linear speed density relationship as shown in this figure, a parabolic flow density model can be obtained by substituting, where all terms are defined as previously. The general form is shown as the figure in this figure, not in the figure that the maximum flow rate represents the high rate of traffic that the highway is capable of handling. This referred to as the traffic flow and capacity, or simply the capacity of the roadway. Traffic density that corresponds to this capacity flow rate and the corresponding speed. So this is the illustration of the parabolic flow density relationship. So the speed flow model, again method to the linear speed density model, a corresponding speed flow model can be developed by arranging. The speed model defined gives a parabolic function as shown in this figure. Note, in this figure shows the two speeds are possible for flows. Q up to the highway's capacity. Q cap, this allows from the two densities possible for given flows as shown in this figure. It is desirable for any given the flow to keep the average speed mean speed on the upper portion of the speed flow curve. When speeds drop below U sub cap, traffic in highly congested and stable condition. This is the figure illustration of the parabolic speed over speed flow relationship. This is the figure for flow density, speed flow relations assuming a linear speed density model. So all of the flow speeds and density relationships and their directions are graphically represented in this figure. So for example, a section of highway is known to have a free flow speed of 55 miles per hour or 88.5 km per hour and a capacity of 3,300 vehicles per hour in a given hour. 2,100 vehicles were counted at a specified point along this highway section. In this linear speed density relationship shown in this figure, applies what would you estimate the space mean speed of these 2,100 vehicles to be. So the solution will be the jam density is first determined from the equation 5.2 as rearranging and solve the equation like this. So in this chapter 5.4, model of traffic flow, one of my group will be report in the next topic of this reporting. So shukran and wasan.